Welcome back. In this video we're going to look at an example of a tangent plane to an ellipsoid at a given point. This is an application of the general equation for a tangent plane of an implicitly defined surface that we talked about in the last video. The problem that we're going to work on in this particular video looks like this. For an ellipsoid given by f of x, y, z equal to x squared divided by 9 plus y squared divided by 25 plus z squared minus 1 equals 0. Find the equation for and graph the tangent plane to this surface at the point 0, 4, 3 divided by 5. The second part of this problem is going to be to find any points on the ellipsoid with a horizontal tangent line. Let's begin our problem by recalling what we know. In particular, let's try to understand this problem. First things first, we recall that for a surface defined by the implicit equation f of x, y, z equals 0, the equation for the plane tangent to the surface at the point P0 with coordinates a, b, c is given by the dot product between the gradient of our capital F function evaluated at a, b, c dotted with the vector that connects any general point on the plane to the specific point on the surface through which the tangent plane passes. So in this case it would be x minus a, y minus b, z minus c, and we said that the gradient will be orthogonal to any vector on that plane, which is quite amazing, so that this becomes 0. And what this means is that we would take the partial derivative with respect to x. So this is the partial derivative where the gradient of this vector is given by the partial derivatives in the x, y, and z components. Here, when we look at the original equation, we're going to do two things. First, we're going to check that the stated point 0, 4, 3 over 5 is on the surface, and next we're going to find the gradient of this function at this stated point. So we'll begin with part 1 by checking that the function satisfies the equation for the surface. We know that the equation for the surface should be that if I put in a, b, and c to the capital function f, that I get 0. So this means that I want to check, and this is, right now we're not actually, so this should be true. We don't know whether or not it's going to be true, so what we're going to do is just kind of follow our nose, so to speak. So here the equation for the ellipsoid was x squared divided by 9 plus y squared divided by 25 plus z squared divided by 1. Well, in this case, z is 3 over 5, and then I'm going to square that, and then I subtract 1 from it, and we would want to know, well, what is that? And we'll see in a second. For those of you fast viewers, you probably see what's happening. I see what's happening here. Alright, so here we go. 9 divided by 25 minus 1. And then we've got something like 25 divided by 25 minus 1. And indeed, the hardest problem that we solved so far is to figure out what 1 minus 1 is, and it looks like 0. So indeed, this point is on our surface. We conclude that the point P0 of 0, 4, 3 divided by 5 is on the surface that's defined by f of x, comma y, comma z equal to 0. Next, when we look at the second thing we were going to do, we were going to find the gradient at this given point. Well, remember that the gradient of our function is the vector containing the partial derivatives, and I'm going to be a little bit cavalier about how I write this. So right now, the gradient really should have 3 inputs in each of the coordinates. So this should be f sub x of xyz, f sub y of xyz, f sub z of xyz. However, just to make it clear what's happening here, however, when we write the gradient, we're going to take the partial derivative of the function with respect to each independent variable. So here, when we take the partial derivative of the x coordinate, this would be something like 2x divided by 9. When we take the partial derivative with respect to y, this would be something like 2y divided by 25, I'm sorry. And then the partial derivative with respect to z would be 2z. And since the partial derivative of a constant is 0, the 1 cancels out in every single one of those cases. And then when we go to evaluate this sucker at the actual inputs that we were given as the point around which we were going to expand this tangent plane, we just go ahead and substitute the values in. So this would be 0 in the first coordinate, or component, I'm sorry. This would be 8 over 25 in the second component, and then something like, 6 over 5 in the third component. And this gives us the direction of the tangent plane. And then we just go ahead and substitute that in. When we look at the tangent plane itself, we now have an equation for the tangent plane, which is the gradient of this evaluated at 0, 4, 3 over 5. And we just said that we were going to dot it with the vector x minus 0, y minus 4, z minus 3 divided by 5. And we said the entire thing should be equal to 0 since the gradient is going to be orthogonal to the particular plane that we're looking at. And then we have here, this is going to be something like, 0 times x, because that's going to be the first coordinate there, plus 8 over 25 times y minus 4. And then we're going to multiply the last component of the gradient, 6 over 5 times z minus 3 over 5. And then some of you might be thinking to yourselves, well, let's make this look a little bit more beautiful by doing some simplification. So this would be 0. This thing right here, I guess we could call it 8 over 25y. And then this would be plus 6 over 5z. 8 times negative 4 is negative 32 over 25. And this would be another negative 18. So 32 minus 18 looks like 50, right? And 50 divided by 25 is 2. Don't trust me on this. In fact, I should not trust myself. So let's go quick check. 8 over 25 times 4 over 1. And then we would add that to 6 over 5 times negative 3 over 5. And then this was indeed 32 over 25 minus 18 over 25. And I think I feel good about that. I think this is negative 50 over 25, which would mean this was negative 2. And then we said the entire thing was equal to 0. And now this is the equation of the tangent plane that we wanted. The major theoretical push here was to say that the gradient of a function is orthogonal to the tangent plane on a level surface. That's the three-dimensional analog of the two-dimensional thing that we talked about in section 11 about gradients being orthogonal to tangent lines of level curves. All right, we're not done with this example yet. After we finished part B, we're going to go on to actually graph this in Mathematica, and then we'll also graph part B in Mathematica. So this gave us part A, which was to find the equation of a tangent plane at a particular point. Part B was to find general points at which the tangent plane is horizontal. So we want to find some sort of point. I don't know what you call it. Could be more than one. Probably will be if it's an ellipsoid, right? And maybe we call those points P, and we're going to look at them as like A, B, and C, such that the tangent plane is horizontal. In other words, when we say that a plane is horizontal, we mean that the normal vector to this plane is in the z direction. And there's yet another way to say that, which is to say that the gradient at the point that we're looking for is some scalar multiple times the vector 0, 0, 1. This gives you the unit vector pointing upwards in the z direction, and then this is the z direction, right? We say the z direction is the set of all scalar multiples times some vector in that direction. So to say that we want to find all points on the surface where the tangent plane is horizontal, that means we want to find all points where the normal vector is in the direction of z, but the normal vector to a tangent plane is the gradient of the function that defines the surface. Well, we already know what this gradient's going to look like. We said earlier that this was going to be something like 2x. Well, in this case, we're going to call the, I don't know if we want to use x or a. We might just use x. It doesn't really matter if we use these. The general equation we said was in terms of x, y, and z. So this was going to be 2x divided by 9. The next one was going to be something like 2y divided by 25. And the last one was something like 2z. And then we want this to be equal to 0, 0, alpha for some alpha. We're not sure what that alpha is going to be to start with. Well, immediately this vector equation comes up with 3 scalar equations. This is one of the really cool things about linear algebra, that a single equal sign actually represents many, many, many scalar equal signs, which is just amazing. So this is now 2z equals alpha. All right, so now we have this concept that x for sure would be 0, y for sure would be 0, and then we're going to have z equals some alpha divided by 2. We're not sure what that alpha is going to be right now. However, we're looking for points on the surface, so we actually have another equation. We want to find now points x, y, z on the surface where the x and the y coordinates are both 0, and then z is non-zero. So this means that when we go ahead and evaluate our surface equation, we're going to put zeros here and we're going to have an unknown z. So this is going to be 0 squared divided by 9 plus 0 squared divided by 25 plus z squared minus 1, and we know the whole thing would be equal to 0. And then we would now say that this is z squared minus 1 equal to 0, and we're old pros at this now, right? This is now going to be z squared equal to 1, and then we can go ahead and take the square root of both sides of this thing. For those viewers at home, what's the square root of z squared? Slowly, don't answer it quickly. Ding, 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 ding. It is the absolute value of z. That's an alternative representation of the absolute value. And then this means that z is equal to 1 or z is equal to -1, which means we have 2 points with a horizontal tangent line, either 0, 0, 1 or 0, 0, -1. And we're going to go ahead and graph those on the Mathematica notebook that we're going to use to verify that this example is legit. We can see that in those cases, we actually have the exact equation for the tangent line, because this would be the gradient of, we'll do the first one first, 0, 0, 1, dotted with x minus 1, x minus 0, y minus 0, z minus 0. Well, we know the gradient of 0, 0, 1 is going to be 0, 0, 2, and then this is going to be dotted with x, y, of course this should be 1, sorry about that, z minus 1. So now the equation for the tangent line is going to be tangent plane, 2z minus 1 equals 0, and another way to say that is 2z minus 2 equals 0. So that's going to be the equation for our tangent plane associated with this one, and the other one we would literally just swap the direction and swap this value, and we'll do that on Mathematica. Let's switch over to Mathematica and see that what we have done is actually too legit to quit. Here we are in Mathematica. We're going to go ahead and graph the surface, which is an ellipsoid, and then the tangent plane to the surface as the given point that we did in part A of the example. So here we'll go ahead and call P0. We'll set it equal to the point that we're going to expand about, which I think was 0, and then we had something like 4, and then 3 divided by 5. And then we'll go ahead and graph the surface. So here we had a contour plot, and we're going to do this in 3D. We'll open and close brackets. So this is going to be the end of the contour plot 3D command. And then up here we call this x squared entire thing, entire thing divided by 9. And then the next one was going to be y squared entire thing divided by 25. And then the last one was going to be z squared. We subtract 1 from that and set the entire thing equal to 0. We need to determine the x and y and z values. I can see by this equation that the x semi-axis is going to be of length 3, the y semi-axis is going to be of length 5, and the z semi-axis is going to be of length 1. So maybe I go from -5 to 5. I think actually I'm going to go from -6 to 6 so that I can see a little bit outside the actual ellipsoid, and that will be helpful when it comes time to graph the tangent plane. So we'll go from -6 to 6. And then just to keep the axes, or excuse me, the box that I'm working within in Mathematica the same, I'll go from z -6 to 6. Notice that I could graph this immediately like this. And there's the ellipsoid, and we see that that y semi-axis is length 5. There it is. The x semi-axis is length 3. There it is. And the z semi-axis is length 1. There it is. And Mathematica actually does meshes in all of those directions. So you can see the, or excuse me, what we would call traces. I'm sorry, the trace. The mesh is a bunch of trace done on one. I have issues with this, so I'm going to go ahead and turn the mesh off. And then I also have issues with the color that Mathematica defines for me. So I'm going to go ahead and say that the style that I want is not the style that you tell me that I should have. So take this. We'll go ahead and say pink because real mathematicians graph in pink. And then we have 0.4 perhaps. Okay, there's the ellipsoid with a mesh off. Next thing we're going to do is go ahead and slap in a base. I'm going to slap a point on this sucker. So here we go. To do this, I'm going to put show, and then I'm going to end the show down here. Remember, show is like a cut and paste of different graphic objects on top of each other. So here's the graphics. Oops, sorry, those would be brackets. And then we'll do a list inside. We'll do this thing in green, perhaps. And then we'll say that the point size on the point we're going to slap on this is going to be 0.02. And then the point that we're actually going to graph is going to be the point P0, which we defined above. What are you complaining about, Mathematica? It should not. Oh, of course it's graphics 3D. What a silly goose. All right, there it is, right? I don't know if green, is green good? Maybe we should do blue. Is that better? It's a little bit better, right? You can see it a little better. Okay, so now we want to do the tangent plane, and the tangent plane is going to be, again, come from a contour plot. We could just use the same exact code that we did up here and change this thing. Look back on your notes to see that the equation for the tangent plane at that particular point was given 8 by 25 times y, 6 by 5 times z, and then of course we said that this was -2 equal to 0. And in this case, we'll let this thing be blue. Oh, it's complaining because I have that thing there. Okay. And then, oh, I should actually name the end brackets here. We'll call this end of the show command. All right, there we go. Check that out. This is pretty cool, right? Actually, it's freaking amazing. So that is the tangent plane. It's the plane that touches right at the tippy top there. There it is. And then one last thing that we might do. You might want to change the size of this sucker. I don't know if we've talked a lot about image size. I think we've done this at least one other video. So image size, we could make this thing into a full image, and that would just make it as large as the screen that I have. So if I shrink the screen, the image size shrinks. The last thing what we might want to do is actually graph the gradient vector to show that the gradient vector actually is directly orthogonal to that plane. So if you look at the gradient vector at this particular point, we would say that it's given by 0, 8 over 25, and the last one was 6 divided by 5, and we did that work in the handwritten part of this video. Remember, a vector needs a tail and a head. The tail of this vector is going to be the point P0. That's where the gradient vector is going to start. And then the head of it is going to be from P0 along the direction of the gradient vector. Okay. So now we're going to go ahead and graph an arrow that starts at P0 and ends at P. An arrow is a graphics element, and it's done in 3D. We'll do this arrow in red, and it's not going to be a point size, it's going to be a thickness. And I think a good thickness is like 0.003. The command for arrow is arrow, and then arrow expects a list of points, and the first point is going to be the starting point, and the end point is going to be the head. Check that out. Look at that. That is directly orthogonal to vectors in the plane. Isn't that amazing? Isn't that really, really cool? That is the tangent vector. What's really cool too, I don't know if I've shown this, if I want to shrink this, I literally just click on the image and shrink it. So this is quite cool. And then let's say that I wanted to get an A+ on a homework assignment that I had to submit. I could print this or I could save it. There are some really, really cool things associated with Mathematica. Yeah. So that is now the tangent plane to the surface at that point. As a challenge to the viewer, I challenge you to take this code and change it to graph the two horizontal tangent planes, the one on the top and the one on the bottom. I'll see you in the next video.